Hi, Calc 3 students. So just to make sure that you guys practice a little bit more, I'm giving you guys two more examples with double integration over polar coordinates. So this one's a little bit more involved because we have to complete the square. And then in another video, I'll do the second one. So the first problem is that we want to evaluate this double integral over the region R of y dA, and here R is the region bounded by two different graphs. So we have this guy, which actually is a circle, but you can see that you have this extra 2x term, and then you also have the line y equals x. So the first thing that we want to know is that we're dealing with a circle. That's the first thing. And we're also dealing with the line. So let's deal with the circle. We kind of want to look at what exactly this region looks. So first, what I'm going to do is I'm going to move the 2x over. So I have x squared minus 2x plus y squared equals 0. And now what I'm going to do is I'm going to complete the square here. So you can see that we're going to have x squared minus 2x. And to complete the square, what you got to do is you got to take this negative 2 divided by 2 and then square it. So tapping into our algebra skills. So that gives me a 1. So what I'm going to do, let me go ahead and fill in the rest of the blanks. So I have the plus y squared equals. So what I'm going to do is I'm going to add this one here to kind of complete the square. And then I'm going to add the 1 on the other side because I can't just add a number without having to do it to the other side as well. And then what you can see is that I can actually factor this as x minus 1 squared plus y squared equals 1. So you actually have a shifted conic, so it's a shifted circle. So if you kind of look at the region, so x and y, you can see that the center is no longer 0, 0. So now the center is going to be moved over 1 unit and then at 0 because there's no movement in the y direction. The radius itself is still going to be 1. So you can kind of see that. I'm going to move over 1 unit over. And I'm going to complete this circle, which is kind of shifted over. Okay, so there's my circle. So this one corresponds with that x squared plus y squared equals 2x. And now we have that line. So this line is just y equals x. We just know how to graph that. 0, 0, 1, 1 is one of the points that you can use to graph it. And then we're just going to draw this line. And basically, the region R is this particular piece. So this piece is the region that I'm taking the double integral over. Okay. So now here's the tricky part. Okay, because this actually, I think, would be considered the easy part. The tricky part now is converting everything to polar and finding the limits of integration. So first, let's start off by thinking about converting everything to polar. So let's try to convert the line and also the circle to polar. Okay, so we wish to convert to polar. So what we're going to do is let's convert this x squared plus y squared equals 2x to polar, and also this y equals x to polar. And it'll make sense why we're converting it like this. Because here, the radius is going to be a little bit different, and let me show you why. So here we know that this guy's going to be r squared, and then x is just equal to r cosine theta by polar coordinates. We can move it over, so we have r squared minus 2r cosine theta equals 0. We can factor out an r, and then we have just r minus 2 cosine theta equals 0. So either r equals 0, well, this is just the pole, so this is not quite the equation of the circle. And then we have r equals 2 cosine theta. So this guy, basically in polar coordinates, represents this circle. And it should look very familiar from what the things that we talked about in Calc 2. So this one represents the shifted circle. So this shifted circle. Okay. All right. It'll make sense why we're converting it this way in a second. Then we have y equals x. Let me move it over here. So y equals x is going to be, in this case, think about what y is. Y is r cosine theta. Okay, whoops, that's wrong. R sine theta. and then x is r cosine theta. Okay. Again, I can move them over, and you'll see that this is silly, but at the same time, not so much, because you quite don't want to divide by r, because r can be equal to 0. So you have r and sine theta minus cosine theta equals 0. You can see that r equals 0 is not really going to give us the equation of the line. So all we have is sine theta equals cosine theta. And one thing that I can do is I can divide this by cosine. And notice that this gives me tangent of theta equals 1. And then if I take inverse tangent, you can see that theta equals pi over 4. So basically, theta equals pi over 4 is basically this y equals x line. So this represents the y equals x, the line. Okay, now why was that useful? Why did we do that? Why did we go through all that work? Well, now it'll help out when we're trying to set up our double integral. Okay, so we have right now our double integral over the region R of y dA. So remember, to convert to polar, you have to take the double integral. Y in this case, when we convert it to polar, is just going to be r sine theta. That's what this y is. And remember that dA, we're going to have that extra r dr d theta. Okay, so here we're going to have this r dr d theta. So this one corresponds with this dA when we convert to polar coordinates. Okay, which is what we learned in class. And now what we want to do is we want to set up the limits of integration. So we need to set up what are the limits of integration of r and what are the limits of integration for theta. And here's the tricky part. So we got to look at our graph, okay? So remember that r is always going to start at the pole, okay? Here's the pole. And remember that we're in polar world. And now remember that this is not going to go from 0 to 1. It's not that. The reason why is because we're not centered at 0. If you remember a circle that's centered at 0, that has a radius of 1, from the pole to any point on this circle is going to be r is from 0 to 1. Clearly, so from 0 all the way to a radius of 1. 0, radius 1. 0, radius 1. 0, radius 1. Now what happens to this circle though, if the circle is not centered at 0? So instead we have this guy. Well, the radius, so if we start at the pole from 0, and then we go to any point here, you can see that the radius is continuously changing. Okay, so we're not centered at 0. The pole is not at 0 anymore. The pole is kind of shifted over. Okay, we kind of have a hinged. So it's going from 0 all the way to whatever the equation of this circle is. And the equation of this circle is what we just found out, this 2 cosine theta. So it's going to go from 0 all the way to 2 cosine theta. That's going to be the limits of integration for r. 0 to 2 cosine theta. And now what about my angle theta? That's another tricky part. So think about how we graph a circle in polar coordinates. So remember, this starts at theta equals 0, theta equals pi over 2, theta equals pi. So notice that we start here. This is at theta equals 0. When we're graphing the circle, we continue on, and then we stop at pi over 4. So remember that this guy is at pi over 4, because the line was theta equals pi over 4. But notice, we don't want to go from 0 to pi over 4, because that would mean that I would want this area right here. That's not the area that I want. The area that I want is this green part. So actually, my lowest theta will start at theta equals pi over 4, because that's where that guy is at. This is my starting point at theta equals pi over 4. Okay, and then from pi over 4, I'm going to circle around all the way until I get to where? Well, I'm getting all the way to pi over 2. So from theta equals pi over 4 to theta equals pi over 2, we're going to have this area, which is the area that I want. So this will be from to theta equals pi over 4 to theta equals pi over 2. All right, so that was the trickiest part. Now after that, all we got to do is just do this integral. So this guy's going to be the integral from pi over 4 to pi over 2. And then the integral from 0 to 2 cosine theta. r and r gives me r squared sine theta dr d theta. We're going to integrate first with respect to r. So we're going to have the integral from pi over 4 to pi over 2 of r cubed over 3 sine theta. This is between 0 to 2 cosine theta d theta. All right, now what we're going to do, let me pull out that 1/3 because that 1/3 is basically not going to really do anything. And we got the integral from pi over 4 to pi over 2. And then I'm going to use the fundamental theorem of calculus. Plug in the first one. You're going to get this 2 cosine theta whole quantity cubed sine theta minus 0. Because this guy, when I plug it in there, will just give me 0. So then you just have d theta. So this guy is going to give me integral from pi over 4 to pi over 2. This guy just corresponds to 8 cosine cubed theta sine theta d theta. And notice that I can take out the 8 again. So I have 8 over 3 integral from pi over 4 to pi over 2 cosine cubed theta sine theta d theta. Okay, and now what we have is just a basic either calc 1 or calc 2 integral. So we have a trigonometric integral here, and all we can just do is just do a u substitution. So we're going to let u equal my cosine theta, and my du is going to be equal to negative sine theta d theta. I can divide the negative over, so you got negative du equals sine theta d theta. Okay, so this is going to be my u substitution. And now what we have is 8 over 3, the integral. So remember, these ones, you can either change them to u, or you can just remember that these belong to theta, not to u. Okay, so now cosine cubed, that's going to be, well, cosine is u, so this is going to be u cubed. This entire thing, the sine d theta, is just basically the negative du. So I'm going to put du right here and the negative out here. Okay, and now what I'm going to do is now I'm going to take the antiderivative. So I'm going to get negative 8 over 3. The antiderivative of u cubed is just going to be u to the 4th over 4. And then between pi over 4 to pi over 2. And these guys come from theta. Okay, so just so that I won't have to write this again, I'm going to plug in the cosine. So you're going to get this negative 8 over 3 cosine to the 4th theta over 4. This is between pi over 4 to pi over 2. And then you don't have to write the theta anymore. Okay, so then what you can see is that now you can multiply this negative 8/3 times this 4. So this is just going to give me 1, and then this one's just going to give me a 2. Okay, so I get negative 2/3. Then we're going to have the cosine 4th theta from pi over 4 to pi over 2. And now all we got to do is just plug this guy in. So we're going to have the cosine of pi over 2. And this whole thing is going to be quantity to the 4th. And then we're going to have minus cosine of pi over 4, quantity to the power of 4. So we know that the cosine of pi over 2 is just going to be 0. This guy is going to be square root of 2 over 2. Okay, and if I bring it up to the power of 4, so we're going to have negative 2/3. Then we have a negative outside. Then we're going to have the square root of 2 over 2 to the power of 4. This negative and this negative becomes a positive, so you just have 2/3. And then we can just go to our calculator, and we can try to figure out what the square root of 2 over 2 is to the power of 4. And you get 1/4. Okay, so you're going to have 2 over 12 or 1/6. Okay, so this is will be the answer for the double integral over the region R of y.